Hi students, this will be a quick review of the speed and velocity lecture. So the first idea, the first concept to understanding speed is that in order for something to be considered moving, we need to compare that object to something else. So things only move relative to other objects. For instance, there's an example here with a book on a table. When you're looking at a stationary book that's just resting on a table, it's not moving compared to you, compared to the table. But if we think about that book moving compared to the sun, for instance, it is revolving around the sun because the earth is revolving around the sun. So really, it's actually moving very, very quickly. It's moving 30 kilometers per second, but only 0 kilometers per second compared to us. So this is a very simplistic example, but the whole point of this is just to talk about how unless you're comparing one object to another, nothing is moving. Technically, the Earth isn't moving if you look at just the Earth, but as soon as you compare it to the other planets or the sun or other galaxies and solar systems, all of a sudden you can tell that it's in motion. This is the idea behind the bus examples that we talked about in class. So now you get to see my wonderful drawings, my depictions of a bus. Despite being a bus monitor, I can't draw a bus to save my life. Okay, so here's Dexter's Southfield school bus, and here is random person sitting on the street. He's just standing there on the street. Okay, so he's not going to get run over by the bus. He's to the right of the bus. So if he is moving, he is not moving, so we would say, at least compared to the ground, so he's moving 0 meters per second. He's standing still compared to the ground. If we have, here's Mr. Kalman, the bus monitor. He's at the back of the bus. The bus is moving forward at 30 miles an hour. And I am also moving forward on the bus at 5 miles an hour. How fast does it seem like to this observer that I'm moving? Well, you would add those two together. You would say that compared to the bus, I'm moving 5 miles an hour. But compared to the ground and compared to the bystander, not only am I moving 30 miles an hour forward on the bus, but I'm actually also moving on top of that an additional 5 miles an hour towards the front of the bus. If I switch directions, right, if I erase this and I was walking from the front to the back of the bus, or in this case I guess I'm diving out of the bus moving 30 miles an hour forward and me moving 5 miles an hour backwards, we would start to subtract those. So that gets us kind of into the idea of vectors, which we'll come back to in a minute. But again, depending on what you're comparing things to, me moving to the front of the bus, I could be moving 35 miles an hour compared to this bystander. I could be moving 5 miles an hour. If there was a bus traveling next to this one, also moving 30 miles an hour, how much would it look like or how fast would it look like I was moving? It would look like I was moving 5 miles an hour compared to the people on the other bus next to me. So motion is always relative. So when we're talking about speed, really what we're talking about is how much motion an object has over a period of time. So we measure that by talking about how far it moves, its distance divided by time. Much simpler, d over t. Distance divided by time. In math, you often talk about how distance equals rate times time. D equals RT. That's usually an equation that people bring up that they've heard about in math class. So rate here is just speed. So it's just a reorganization by multiplying t by both sides to get it out of the denominator. So S, that was a t, ST equals D here, or D equals RT. Same thing. Same equation, just in a different order. You have to include units of both distance and time. So for instance, in this example here, if I just wrote 30 what, right? What are we talking about? Are we talking about 30 miles an hour, 30 miles a second, 30 light years? Like what's that's not a measure of speed anyways, it's distance, so that would throw you off. So you need to have units in every instance. When we're talking about these two ideas here, people get very at first you think you get it and it makes total sense, but then you'll get to a problem, we'll ask a question, and it's going to seem a little confusing. So don't get fooled by how simple these both seem. Instantaneous speed, at its simplest, is that essentially you're not traveling at the same speed in any one instant compared to another. When you're running across a track, at one point in time, you're moving really quickly, then you slow down, you kind of falter for a step, you might stumble, then you speed back up. So with every step, you're moving a slightly different speed. So your instantaneous speed is whatever you're moving in that exact second. So the easiest way to tell this would be to look at a speedometer, right? And every second, every time you look at that speedometer, that's how fast you're moving in that instant. The average speed is essentially how fast you went on average over a total trip. So the misconception is that you could take, usually to calculate an average, you take, X, Y, and Z and divide it by 3, right? 1 thing, 2 things, 3 things, divided by 3. So theoretically, couldn't we find our average speed by adding up instantaneous velocity 1, instantaneous velocity 2, instantaneous velocity 3, and dividing by 3? No, we will never find our average speed by doing that. Because how do you define an instant? If you travel for 4 hours and you look at your speedometer 4 times and you are moving 50, 50, 50, and 50, those 4 times, you would think, well, I can add up all those 50s and divide by 4, I'll get 50. My average speed was 50 miles an hour. But here we're talking about looking once an hour at your speedometer. What if between, this is at time 0 and this is at time 1, what if between there, for a little while, you sped up to 80, then you slowed down to 30, then you sped up to 100 because you wanted to get there faster. Then the cops were on you, so you had to slow down to 20, right? You got pulled over. You have to sit by the side of the road for half an hour while you get yelled at and you get a ticket, right? So all of those different instants that happened between the time that you looked at the speedometer here and the time that you looked at the speedometer here are ignored if you're going to try this method. So maybe you just need to look at the speedometer every minute. But even then, in between minute 1 and 2, you might slow down for a second or speed up for a second. So you're getting a little bit more accurate, but not much. Well, couldn't you look at the speedometer every second? Well, over a 4-hour trip, that's going to be 4 times 60 minutes times 60 seconds. That's going to be a lot of data that you have to look at. So you'd be pretty close to accurate, but even then, even looking at the speedometer every single second, in between second 1 and second 2, things theoretically could have changed a slight amount. So it still won't be completely accurate. So I like to say that within a second, there is infinite time, because we can keep taking that 1 second and make it 0.1 second. Or make it 0.01 seconds, or make it 0.001 seconds. So we could just keep going and going and going. And no matter what, you will never be completely accurate because you can't actually find your speed, your instantaneous speed at every single instant. So that's a long explanation of explaining why we calculate the average speed being your total distance covered in the total time that you traveled. So you traveled, despite the fact that you were going 50, 50, 50, and 50 for those 4 hours, so you think you might have traveled 200, right, based on this data. Wrong. What you actually traveled was only 100 kilometers, or sorry, you traveled 240 in those 4 hours, because in between there, you sped up for a little while. So you have to take the total distance divided by the total time, otherwise you're not going to be accurate, because each of these hours, who knows what happened in between there. So that's why this starts to get a little bit more confusing. Velocity, there's this sentence right here, velocity and speed are used interchangeably but are slightly different. Here's how I want you to think about speed and velocity. They're exactly the same, except velocity includes a direction. It is just speed with a direction. So if I want to change 60 miles an hour, which is my speed, into a velocity, I would say 60 miles an hour north, or 60 miles an hour south. Or if we're talking about doing something in class, it might be to the right, to the left, up, down, away from the group, towards the group, right? Any direction that you throw in there. So there's 3 different ways that you could change your velocity, which I'm jumping down to right here. You could speed up, you could slow down, or you could change your direction, right? Those are the 3 ways you could change your velocity. You could change the speed, or you could change the direction. To have a constant velocity, you not only have to go the same speed and the same direction. If you change either one of those, you've changed your velocity. So a good way to represent velocity is to use these things that we call vectors. And we already had a little practice with that up top here where we were talking about the bus. Essentially, a vector is kind of really it's just to simplify, I'm going in that direction. And the length of your arrow is supposed to describe the magnitude of your speed. So this arrow, being longer than this arrow, would mean that I'm going faster in option A than in option B. And if I gave you a key, if I was to say essentially like 1 inch equals 10 miles an hour, so 0, and this line here is 2 inches, and this line here is 1 inch, we could calculate how fast I'm going in each scenario. If this is 2 inches long and 1 inch equals 10 miles an hour, we're just talking about a scale here, like on a graph. That's 20 miles an hour. In this case, it's just 1, okay, so 10 miles an hour. Now what happens if we start to combine these things? If I take a 2-inch vector and add it to a 1-inch vector, this one's going to be pushing this one. All of a sudden the resultant velocity would be 3 inches, or 30 miles per hour to the right. If, screen's not moving down, there we go. If I had my 2 inches and then my 1 inch going that way, that would tell me that they're going against each other, so we would subtract. So it would 2 minus 1 is going to be 1. Which direction is going to win? The bigger one always wins, so I would my resultant velocity would be 1 inch in that direction, or 10 miles an hour to the right. If, this was 2 inches and this one was 3 inches, well, that's going to flip me around. If this is me and this is like wind, right, a headwind coming and slamming into me, it would turn me around. It would result in me going backwards in this direction 1 inch, right, a 1 inch vector, so 10 miles an hour to the left. Now it would flip me being the object around. So kind of a trickier one is, what if we pretend like this is an airplane, right, traveling at, let's say, 10 inches, so very fast, 100 miles an hour, and it has a side wind of 1 inch. Well, actually calculating the speed that would result from this would be quite difficult, but we can pretty easily figure out what would happen to the direction. If you were running down a field and you get hit from the side, or if a wind pushes you from the side, do you automatically just start going like that? No, of course not. It would have to be a much stronger wind than 1 inch vector, right? You'd have to have a much stronger force there. So instead what happens is you just slowly start to veer off in that direction. You're still making forward motion, right? And it probably wouldn't even be that much. It would probably just be something kind of like that. You would veer slightly to the left, but you would still be having most of your forward motion. So essentially, the two motions would combine. With any kind of situation like this, I wouldn't ask you ever to calculate the speed or to calculate the velocity, but more just to explain what would happen to the direction. So just a couple of quick things to remember. Motion is always relative. You can only say that something is moving if you're comparing it to something else. Instantaneous speed and average speed seem very simple. How fast you're going in any 1 second, your average speed over an entire trip. Because you don't know your speed at every single instant, since technically an instant is something undefinable, you can't just average all the various speeds that you have. So instead, you have to talk about your total distance covered and the time that you traveled it for. So even if you are going down to the Cape for the weekend and you pull over on the side of the road for half an hour, that half an hour is a 30-minute chunk of time where you're not moving, where your speed is 0. Therefore, that 30 minutes must be included when you're calculating your average speed, because for those 30 minutes you're going 0, 0, 0, 0, right? So that has to be included. Total distance divided by total time. Velocity is just speed with a direction, and you use arrows, or also known as vectors, to help you visualize and describe velocity, since it's a little bit more complicated than speed. That's all for now.